All right. Hello, everyone. I think we can begin. My name is Ndi Mamunur Rashid. I am a second year PhD student at the Warner School of Education, University of Rochester. I am also an NSF research trainee on virtual and augmented reality. And I have another identity. I am also an alumnus of NYU. And our today's speaker is also from NYU. So we already have some sort of connection already. So before I introduce the speaker, I just want to thank everyone for joining us for this Voice of XR and Mary and Mabrina Studio X speaker series. The series is made possible by Kathy McMorran Murray and the National Science Foundation as part of the interdisciplinary graduate training in science, technology, and applications of augmented and virtual reality at the University of Rochester. So let me introduce today's speaker, Dr. Chi-san. I hope I pronounced your name correctly.
Perfectly.
Great. So I'm doing a good job already. And Dr. Chi-san is an assistant professor at Newark University. Before joining NYU, he was a research scientist at Adobe Research. He received his PhD at Stony Brook University. His research interests are in VR, AR, perceptual computer graphics, display, and computational cognition. And he has received like many awards, like Best Paper Award, Best Dissertation Award, Honorable Mention Award, in so many places. I cannot mention all of them. All right. So the floor is yours, Dr. Chi-san. And for the audience, you can post your questions in the chat. We will have a Q&A session at the end as well. So feel free to post your questions whenever you have any. All right, and also this session is being recorded and will be available to all of you later at the Studio X website. So Dr. Chi-san, thank you for joining us today.
Yeah, thank you everyone. Thank you, Manuel, for the very warm introduction. And on the other hand, actually, a lot of research I'm going to talk about today is actually have a great collaboration with the University of Rochester as well. On the other way, right? So yeah, so just to start my talk with this probably very popular device that everybody see, right? So new devices are releasing, they look fantastic, they have a great resolution, perfect quality, perfect brightness, right? But while I was skimming through the website, I opened this, right? So and then there's a very little tiny bit of some words here that probably not many body see, right? You could not even see that if I don't zoom in, right? So this line basically says this kind of device is capable of running for 2 hours on a single charge, right? So we always say in the future of virtual augmented reality, that could be a new medium for like 24/7 human-to-human communication, right? That should be replacing our phone for the future generation of human-to-human connectivity. However, the connectivity are not supposed to last for 2 hours, right? And then you need a recharge. That's not how our mobile phone today works, right? This is starting to be a big concern, so that you even need this kind of external battery and all that, right? So this is the starting kind of issue that I want to bring. Why they only last for this short amount of time, although there are so many engineering efforts is putting on that, right? So this is an anatomical image of the typical XR device, right? The design typically is very complicated. It by itself is a computer, right? So the computer has very high quality display, trillions of pixels right now for micro LED, right? So it also has this data transmission, right, that use some cable to transmit from this computational resources, which delivers a high quality computer graphics with GPU, CPU, all these processors, right? Because there are so many different components, it's becoming not like our smartwatch, but rather a monster computer. That's why the portable battery can only last for 2 hours, right? We want to ask this, right? So it consumes a lot of energy from the display, from everything. But is all those energy consumption actually meaningful or useful, right? But of course, all of them are meaningful and useful because they are very carefully engineered, right? So, but what we actually want to ask, are they all humanly meaningful? Meaning, what is the power consumption that cannot be perceived, right? In general, right? So this is a question we want to ask, right? So that basically motivate some of our research on first one is a human perceptually aware virtual augmented reality system, how to understand human perception to deliver a better system that's more meaningful to human and more efficient in general. And also on the opposite side, right? So we want to also leverage those devices to improve the human performance, right? How do we make drivers safer, make a video game player have a better performance with the help of virtual augmented reality? There's a side discussion on how to understand about physical of human muscles in other VR/AR settings. These are just sample research. Due to time being, I cannot fully cover all of them, right? So I will talk a little bit of some of them. And essentially, the research umbrella that we do is we want to introduce the cutting edge neuroscience discoveries from the science to be applied system, right? What is the human nature? Can we better understand it so that we can transfer this understanding to the computational algorithm that makes not only VR/AR device better, but also human better, right? So we build this algorithmic bridge from those discoveries, right? So if anyone here study neuroscience, vision science, right? So a lot of background is we want to understand the nature, which is a correlation between factor A and B, sometimes a human. We want to also understanding in a more fine-grained way, in a numerical, algorithmic, and data-driven way, so that we can quantitatively optimize the system, right? To bridge the science and applied science. Right. So the first thing we want to talk about is perceptually aware XR system for longer sustainability. So I want to start with this picture. Probably many of you have seen that, right? So it gives us an argument of what really is a color that we see, right, as a human, right? So different people give us different answers on what exactly is the color of this dress, right? Why we answered it differently? Because people understand color differently. That means the way we understand color is imperfect, right? So we do not know what we are actually perceiving. Because we are humans, we are not machines, right? We are not perfect in perceiving things from the eye. We can only approximate, right? So why is that, right? So as a microscopic retinal image is this, right? On the left, you can see this is a human eye. Let's say at this very moment, I'm looking forward. On the right, the green dot shows where my gaze is currently, right? So this is an anatomical image of the human retinal receptor, right? Different colors indicates 3 different color receptors. We have 3 of them, which are indicated as long, short, and medium cone receptors. Each of them are responsible for understanding colors at different wavelengths range. The long is responsible for receiving like a reddish, and then green for medium, with for low wavelengths, right? A different color notation and anatomical image indicate different types of cone cells, right? This is the anatomical image in the center of the retina. And then at this very moment, that means, oops, sorry. I'm using my mouse to control the slides right now. Okay, so this shows a image on the peripheral vision, right? In the peripheral retina, you can see several interesting things, right? You can see we have way sparser photoreceptors on the retina to help us collect color from the eye. And meanwhile, different type of receptors also reduces in a different way, right? So as a biological fact, this may tell us actually our color sensitivity across our retina probably is not consistent, right? Because we have less information collector in the peripheral retina. We have more collector in the fovea. The more information you collect, the better we are understanding color, right? So this gives us a probable indication that maybe in the peripheral color, our understanding of color is limited, right? And then that said, maybe if we change the color in the peripheral vision, if we put this on your VR/AR headset, and this is actually your eye, maybe you do not notice any color change in the first place, right? The question becomes this, right? So why do we bother doing this? Why do I give you a different color image? For what reason, right? So we show that by changing the color of your peripheral vision, we can achieve 2 goals. The first is by changing that, we hope you do not notice any difference, because in your peripheral vision, we think you have studies in the scientific fields also show that we have low color sensitivity in the peripheral vision. And the second thing is we want to show you actually this can significantly reduce the power consumption on an untethered VR device so that it can make your battery last longer, right? There comes down to two questions, right? Why it saves power, how to make it imperceptible, right? So for the first one, this is a microscopic image actually taken by my Rochester collaborator, Yu Hao, which is also co-author of this paper, right? So we purchased a microscopic scope, and then we put this onto the iPhone, right? And then we use the iPhone to take a picture of the screen. It's an LED screen, right? So you can see three pictures here, right? On the leftmost, that is what we saw if we render a pure red color on the screen. On the one hand, I think it's a 10x zoom in, you see this, right? So as we all know, on the LED display, we have three channels, R, G, and B, right? By tuning different levels of three colors, we can render different images on our mobile phone, and similar to XR display as well, right? In the middle, we show how it looks if we only render a green color, which is very normal, right? So as you can see, do I have a laser pointer? Yeah, so over here, right? So you see the green channel is on, all the other channels are off. Here you see only the red channel is on, all the other channels off. But the troublemaker now becomes the blue color, right? So let's say if I render a pure blue color onto XR display, this is what you actually see from the macroscopic image. Is that because blue color, as we probably all know, has very low wavelengths, that means it contains very high energy, right? Low wavelengths typically signals contains high energy. And then to make sure, there are multiple engineering reasons to make this display last longer and all that reasons, we need to turn on a little bit of red and grayish to render the actual pure blue color on the LED screen, which is very broadly used in many VR AR headset. For example, the Apple Vision Pro is a micro LED, if I remember correctly. They have similar mechanism. Then this is the problem, right? Of course, the more light you turn on, the more power it consumes, right? Study has found that this kind of display consumption on a VR headset can consume more than 40% of the whole battery usage, right? But meanwhile, giving different colors may actually consume different levels of power, right? So the power consumption, which is a major consumer of the battery, actually is related to what color is being rendered, right? And then if we can manage to have a way so that we manipulate your peripheral vision, which is gradually here. For example, you can see versus the left, your peripheral vision gradually change to some warm-ish kind of color, right? But our study found that you actually do not see any difference if you actually wear the VR headset and watch the right versus the left. We ran this study on the exhibition at the SIGGRAPH last year, probably almost 500, 600 people. Almost nobody realized that the left and right is actually different. If you actually see that on the near eye VR display. Now you can obviously see that because you are viewing that from far, you don't have peripheral vision, right? But meanwhile, on the right, you can save about 27% of the power usage for the entire display, which can significantly increase the battery life of your wireless VR headset to make it last longer, right? This is what we achieved. The question is how, right? We want to formulate this problem in a mathematical and algorithmic way, right? So this is a basic representation. Okay, no rocket science here, no proof here, but it's very easy to understand. Concept is this, right? Let's say the X is the original color, like a video game or video that I want to render. I really want to, for each pixel, find a perfect sweet spot, new color, such that this color can minimize your power consumption, which is annotated as P, right? But we cannot infinitely do this because what's the best strategy? The best strategy is turn off your screen. You don't see anything, zero power, great, right? But that's not the goal. The goal is we want to have free launch, which means we want to reduce the power such that the change is unnoticeable to the vast majority of our population, right? And then we can have a low value of power without being noticed. That's an overall formulation we want to achieve. Achieving this actually with our data on both human data and physical electronic data, we show that this problem can be a convex problem. So what's the art of convex is that if you solve the arc-mean problem with a convex problem, you can have a closed form solution, right? There's no local minima like machine learning problem, right? There's only one single minimum. And then we can convert this formula, closed form formula, to the GPU, so that the GPU can actually reduce the power in runtime without consuming a lot of new algorithms in real time, right? The first question we want to see is, what is a subset? So that I give you a color, I give you where this color is rendered with the eye tracker. I want to know what's the indistinguishable color distribution. Okay? For those of you who are not familiar with this, I can give a very brief introduction is for how the human perceive color. This is still open science today. There's no agreement on how exactly we perceive color, but one of the color space that we describe how human perceive color is by the DKL space. Right? So as I mentioned before, we have 3 photoreceptors on the retina. The way people describe how human perceive color can be this, right? We are not computers. We do not perceive color by RGB and adding them together. The brain perceives color in a more human way, which is we have the signal captured on the retina for the 3 color lights. We compare their difference instead of adding them. In one dimension, we try to compare how much do I perceive here and how much do I perceive here. What's the difference between them? It's easier to compare difference than adding things in the brain, right? So one of the dimensions compare the difference between them. The other dimension is compare this versus the sum of them, which is a side story. That forms a new color space, which is slightly different from what our familiar RGB color, right? Hypothesis in vision science suggesting this could be one good color space to describe what is a color, right? And our goal becomes this. Let's say I have an original color, which is here, right? I want to find a range such that if any color in this range is rendered on the screen, you cannot tell any difference, right? And then this is some side note I want to save time from, right? So such that we can find a new color within this range, which minimizes your power usage, right? This is a major goal that we want to achieve. But understanding this range is a very complicated process, right? So it's a function of not only the original color, but also where this color is rendered on our VR or AR display, right? Because as we said, we have a lot more information in the foveal vision than the peripheral vision. That means our sensitivity in peripheral vision is low. That means the radius of this range should be bigger in peripheral vision because we have less information. We are very bad at telling color A versus color B, but we are probably better in the foveal vision. So we need to conduct a human psychophysical study to understand this difference, right? So then that helps us to form this problem, which is first is the original color. And here is a variable that's commonly used in vision science called eccentricity. By eccentricity, we mean it's an angular number. So eccentricity equals to 0 means where this color or this pixel is exactly in the center of my eye. That means it's a foveal color. When the eccentricity gets bigger and bigger, that means the pixel is getting to my peripheral retina, right? That means I could be probably worse in telling the color. And because the human eyeball is a ball, instead of describing by X, Y, Z, it's easier to describe by angles, right? So that is a polar angular space, right? And this is distance in the periphery. And then some prior neuroscience study found that this range can be described or approximated as an ellipse shape. Ellipse, of course, it has 2 dimensions, right? So alpha 1 and alpha 2. We want to find those ranges by learning the function that does this mapping, right? So we did a very large-scale human psychophysical study with a VR headset. So what we did was this, right? So as you can see, this participant was wearing a VR headset. We asked the person to look forward, and we render 4 color patches, right? One of the at different eccentricity, right? At very near fovea and farther for periphery. One of them has a different color. We asked the participant which color appeared different to you, right? So let's say if I can still very well perceive the color, I can give you a perfect answer. My answer is always correct, right? If I am starting to being not able to tell the difference, I may do some random guess because I have to give the answer so that I get my compensation and finish my study, right? So I have to keep doing. If I really cannot tell, I just randomly click a button, right? So we can run probabilistic analysis to figure out the moment when people start to do random guess, right? So that's a moment we want to figure out. A natural question is why 4 patches, right? The easiest case, of course, is the 2 patches, but 2 patches, that's a logistic problem, right? So which one of the color has a different, which one of the patch has a different color? That's a wrong question to ask, right? Because clearly one of them must be different. So we just use a 4 number. And then with a very thousands of trials of human study to do this, we have a statistical analysis to figure out this function, right? So now you can see by changing to different eccentricity and the center color, we learned a function so that I can predict what is the range of the color that human cannot tell any difference when this color is rendered on my retina, right? So this is the function that we regressed overall, right? As a visualization. And of course, because we mentioned this is an easier color space to describe human perception. Essentially, we need to control the monitor, so we convert this color space back to RGB, which is an easy control for algorithms and GPUs, right? So this is a linear process, very easy. So we can visualize that this is a range that people do not tell any difference, right? And also, this is the first question, right? So now we can know if you go back to this original formulation, right? So now we know this. But on the other hand, we need to know this, right? So what is a better color that reduces the power consumption, right? So again, my great Rochester collaborator, Yuhao, kindly take this measurement into this research, right? So basically, he developed this kind of sensing device that can measure the current value of the OLED display. We take out the display from the VR headset. Literally, we bought a similar display to the VR headset. We connect to this measurement device, and when we use computer to render different colors on the screen, and we measure the power current value, which is here, right? As you can see, while we are rendering different colors, you see that goes up and down, that the power consumption is really physically different from this measurement, right? And this shows the overall consumption. This is the current value. As you can see, the amplitude is pretty stable, right? And we collect a lot of this data. And then interestingly, we saw that the correlation between the color and the corresponding power consumption is almost linear, right? So, and then like this. And then we regress a very simple linear function so that if you give me the RGB value, I can tell you how much power does it consume, right? And then remember we said the power of the color sensitivity is an ellipse, convex shape, right? Now, because the power function is a linear function, it becomes a level set, right? Now this original optimization becomes this simple problem that give you an ellipse, give you a length of line, which line has the lowest value overall, right? That becomes finding the convex intersection between the ellipse and the line, right? That's an easy high school problem in mathematics, right? So we all can write a formula easily. I can write a formula right now, and then it doesn't require any additional data, machine learning. We don't need all that because this function was pre-learned as a characterizable function. And then we convert this formula into the GPU graphics pipeline. And this automatically takes care of the color so that they can minimize the power, right? So we can turn on, we compare our method with alternative approach that we go through. And we actually live exhibited this paper at SIGGRAPH in Los Angeles last year, probably with hundreds of participants. Almost none of them can tell the manipulation, although our physical measurements show that they can save about 10 to 25% of power. The average is about 15, depending on your power content. Let's say if you give me a black image, yeah, it's a best already, nothing we can do about it. So the power saving rate is a content dependent kind of function, right? So we analyze in a very large scale data set. This is the power saving natural image that we can achieve. Right? Additionally, more recently, we had this collaboration as a follow-up that because we have limited color sensitivity in the GPU architecture, the data transmission between your memory and your process is very heavy because we need, imagine if you're playing a video game, right? So every frame is an image. Even in VR, that we need to transmit this very high resolution stereo image 90 times a second. right? So the bottleneck is not only the power consumption, but actually how the wires in your GPU can have the bandwidth to transmit this amount of data, right? So reducing the power, the data volume can significantly increase the transmission between your processor and your display. So we have this collaboration that actually adapts the bit depth of the frame buffer, which is a image on the screen, adapt to the power sensitivity. Let's say if I cannot tell the difference between two colors, why do I use 16-bit color? I can use 4-bit color. That can reduce our power volume taking, right? So we show that it can reduce about 66.9% of usage, right? Similarly, we can extend this idea to this machine learning as well. Not sure if anybody have heard about this recent popular neural radiance field, Gaussian splatting. It's a concept that uses AI so that you can capture a few images, and then I can give you the new view from anywhere by a machine learning model, right? As you can see, I can only take a few pictures, and then I can synthesize any view that has never taken before. So this shows a very good promise in future to teleport a physical space in VR by only taking probably 10, 20 pictures. And I train an AI model. This AI model can help my VR to see this physical environment from anywhere. This is different from this virtual environment because in virtual environment, artists can design the scene. But for physical environment, the only input is the pictures. You cannot feasibly capture every single view, but AI can help you do this, right? I wouldn't go through these details. It's a very large computer vision research community. But one of the major applications, why do we do this, is, as I mentioned, we want to teleport a physical environment by VR to the different users in remote. It's a good dream, right? But we test it. This is what happens, right? So if we really use this technology, at least back then, directly in VR, this is 90x speed up. In our experiment, yeah, the GPU wasn't as good as today, but it's comparable, right? So it takes about 90 seconds for the AI model to help me understand a new view, right? So, but in VR, what do we want? We want 90 frames per second. We want stereo. We want 4K images, right? So this AI-based neural rendering or neural field technology was very far from what we actually wanted, right? So by considering human visual cognition, we actually can reduce, we realize that actually in these AI models, 98% of the computation doesn't really matter to human because our eye is so bad. Many of the artifacts many of the effort that try to increase the image quality is not perceivable. We can actually, if I have an eye tracker, we can actually only use the AI to compute those components that are meaningful to human. 98% are pointless to the human eye. Not saying they don't increase the video quality, but actually they cannot be perceived if you use them for VR, right? And we can, considering this, we can develop a new AI model. This model can achieve this AI-based rendering with 20 milliseconds per frame. That gave us about 50 frames per second with the GPU at that time, right? And then I wouldn't go through in detail. Basically, we understand how the human retina perceives things across, as I mentioned, eccentricity, and we train different adaptable AI model so that this AI only learns those pixel values that are perceivable by human, right? So sometimes in the far periphery, the neural network compute very low quality computation, but it doesn't matter because the human eye cannot see that. We are only interested in delivering what matters to human in VR, right? That can significantly improve the performance so that they can achieve. And this is some example, real-time example that I took probably 20 pictures of the room. And I can use this model to train the other user, which is very far, can see this room naturally with very fast performance, right? This is one of the research that we did over here. As you can see, the philosophy is that if we can convert neuroscience, cognitive science discoveries into formulas, into algorithm, into AI models, we can significantly increase the performance of VR, AR display, especially when they are untethered. We can reduce the power usage. We can make the rendering fast. We can make AI models adaptable to what human can perceive and ignoring all those that are meaningless to human eye. Right. This is the first line I like to share. On the other side, I also want to share another way that we think about the opposite. Right. So essentially, what we want is to use this VR AR device to make the humans as a superhuman to let us complete tasks more faster, safer, and all that, right? Imagine this situation, right? So imagine you're driving a car, and at one strange moment, there is a pedestrian appear in your peripheral vision, right? This is a very dangerous condition that can save a life if the driver reacts, analyzes this target faster, right? So we want to ask, in this type of scenario, if the car has a augmented reality display, can this create a superhuman performance so that this driver can brake the pedal faster to save a life, right? Than without augmented reality, right? And that said, we want to understand this problem of how much does it take our brain to process visual information so that we can make our decision and action, right? So this is what we did actually using a VR headset. We run about 14,000 human trials, if I remember correctly, the exact number, of people looking at targets on a VR headset, right? We use the eye tracker, as you can see from here, right? So basically ask you to fix in the middle and then look at this object in your peripheral vision as quickly as you can, right? But we are humans. It always takes us time to process where this target is, what this target is, so that I can take my action, right? And then as a visualization of the data that we have, what we acquire is this, right? So imagine the x-axis, this shows the time propagates, right? And then from, probably you can see from, ignore the others, right? Just look at this green line first, right? The green line basically shows where, maybe a little bit second, right? So the green line shows where our eye is, right? As we are familiar with the eccentricity concept, right? At the very beginning, my eye is in the middle, and suddenly there's some object that appeared. And I need to analyze where this object is, what that is, so that I can take action. At one moment, we make the decision that I should look at this target. And then our eye suddenly quickly moved to the periphery, right? So the eccentricity goes higher. That means my eye rotates to the periphery, right? And then this is the velocity from the same data as well, right? So what we are very interested in this range, this yellow range. So this range is between that target appeared and our brain makes the decision to look at this target, right? And how to accelerate, if we can make this one shorter, humans can take actions much faster by making decisions more efficiently, right? Because it takes your brain less time. So we want to understand what is the correlation between the image content and your reaction time. So we borrowed an idea from neurological mathematics, right? So it's called drift diffusion, which is not a diffusion model that I'm really familiar with for generative AI. It's a completely different things, right? It describes, it simulates a cognitive process that over time, so let me go over this before. This is time. It simulates a brain process that we accumulate confidence of the event that appear in our eye, right? So we keep accumulating the confidence. When our cognitive confidence reaches a threshold, which is a bar, okay, we are confident enough about this event, so we take actions, right? In a mathematical way, we can simulate this as a random walk that we keep accumulating the confidence, and now we are confident enough, we take actions, right? This is simulation, but because this is a random walk, right? So as a human, the major difference between human and computers is even if we ask the same person to do the same thing again and again, our performance, our behaviors of repetitively do the same thing will even be different. Not even saying different people doing the same thing might be different, right? This probabilistic stochastic mathematical to give us this description that because this is a random walk, if I collect enough data that can describe with a random process, what's a general population distribution of performing this task, right? So I wouldn't go through the detail. In any sense, we collect a very large number of data so that we understand the correlation between your image features. Let's say how bright an image is, where the target is, let's say in a virtual environment. That influences your reaction time, right? And then we apply this beyond VR and AR. We also apply this to several applications. Why this time matter, right? So probably much easier to understand scenario to many of us is kind of gaming scenario. This is a collaboration with NVIDIA. So we got this problem actually from a professional esports player, right? So this is one video game. For us, it's for fun, but for professional esports, it really their performance metric is that they are doing this task that as a team player, you may be in this team or this team, right? And while performing this task, their job is the following, is that if I'm on this team, I'm trying to analyze all the frames on my screen that I see to quickly spot the opposite opponent team as early as I can so that I can move my mouse, take the action as early. Whoever do that faster can win this competition, right? Identify where your target is, quickly take actions, right? Which is simulation for also driving tasks as well, which we will see, right? The question we ask in esports content is, the task is the same if we are on both teams, right? But is this game fair between them? As you can see here, this team versus this team, they have different skins and different appearance overall, right? So our model actually can tell you that if you are on this team, the people's reaction time is 1 frame faster than the other team, than if you were on the other team, right? That causes some sort of computation unfairness in terms of cognitive reaction time. And the fun fact, we searched the professional esports competition data set. This team has about 56 to 58 winning rate than the other team overall, although with the same player, right? Now seeing this cognitive reaction time is the only reason, but still, while designing these computation tasks, considering cognitive fairness in people's performance is really important, right? And more recently, we applied this reaction to this augmented reality driving scenario. Probably if you buy the car today, many of the cars have this head-up display called HUD, right? Basically, they project some information in front of the driver so that the driver can always see the speed, maps, everything projected in front of. I don't have to use my eye to watch the dashboard, which distracts me, right? It's supposed to help drivers so that it doesn't distract me from watching the dashboard. But the question we want to ask is the following, right? So does it cause this problem that drivers' eyes are always on this virtual layer so that their eye moved away from the physical environment a lot, right? Does it cause any driver problem so that if I don't have this augmented virtual layer, my eyes may naturally search in the environment, right? See where's the pedestrian, where's the car, when should I take the break? But because my eye is consistently fixed onto this virtual layer, does it influence my driver performance? And if so, how do I improve it, right? So we leveraged our model to study the human reaction time in 3D so that we can provide guidance of where and how much information you should project on your head-up display, right? So I wouldn't go through details, but if you're interested, I'm more than happy to answer any questions around that, right? So basically optimizing the virtual layer for a driving augmented reality, which is hot, is another question, right? So how do we design this virtual layer so that it maximizes instead of lowering drivers' reaction to pedestrians appear on the road with the help of augmented reality? We can even show that with this optimized design of the head-up display, drivers' reaction to pedestrian can even be faster, even though they focus on this virtual screen, right? Then without it. So this is another application that we did more recently, right? These two lines basically summarizes our research on 2 ways, right? So Once we understand the human perception in a formulated machine learning and algorithmic way, how to optimize the system. And on the other hand, by knowing this, can we optimize the AR, VR content so that it can create a super performance of human that actually helps our life, right? Then just entertainment too, right? So it can augment into this physical world, can make the driver safer, can make computations fairness more fair, and all that. It's the side of the inverse question, right? How to use VR and AR to help human, right? As some side notes, right? So beyond visual perception, right? So we are also interested in human physics, biophysics, right? So we are interested in beyond retina. We also study human muscles while playing, while in this VR and AR scenario, right? So this is a condition that you probably seen, right? So if you use this VR headset, the difference between VR headset and a keyboard monitor control is that we frequently use our head to look around, to look up, to search things, right? And then many YouTube video players, even there's a major complaint for the new device is that they feel like a neck pain after using that because the device is so heavy, right? Why this heavy device making our neck uncomfortable? Why, if when we don't use VR, AR, our neck feels fine, right? So the reason is, as a human, we are so well evolved such that our neck muscle design is perfectly designed when we are looking forward. It has like all the muscles on the neck is at minimal tension so that they are most relaxed. So we feel very comfortable while looking forward with a head weight distribution, right? The human is perfect. But with the introducing this VR AR headset, what happens is we are adding a peripheral device onto our head. What it changes is not only the weight, but also where is the mass center. It shifts the head mass center from the middle of the head to a little bit forward, right? That's that even when we are using very natural viewing, let's say look forward, it already introduces additional neck burden because of the VR AR weight design. That's why we want a lightweighter. But however light weight the device is, it always shifts the mechanical mechanism that gives your neck additional burdens, right? So we want to design some better interface so that the position of the object can reduce the neck tension, make our experience more comfortable ergonomically, right? So we use this sensor called electromyography. It's a medical device, but it's also being consumerized recently, right? So basically, this senses the electric signal in your muscles activity. Whenever it generates some tension, it generates some electric signals, right? That can sense the signal. And we put it through all the muscles around the human neck. By using a given VR device, we ask the user to look around at different poses. And we have a machine learning model that can, this is roughly the input data of this signal. You can see they are massive. It probably doesn't mean anything by seeing this, right? But with some measurement, and machine learning approach, we have a real-time CNN that converts this random noisy human data to the head rotation degree, and also this amplitude of the electric means the burden that introduces. Let's say if imagine your muscle is a spring, right? So whenever you stretch the spring, it generates more muscle electric signals, and that means it's additional burden, right? So we want to understand the correlation between your head pose while wearing this VR headset versus the tension, the physical tension that it generates in your neck muscle that controls your head, right? This is the biophysical ground truth measurement from the actual human. So we can treat this as a real signal, and then we calculate the amplitudes and do the conversion. And then later what we do is basically, let's say if you were to design a VR game to design where the target or user interface, right? So where should you place your targets so that it can minimize the neck workload of the human while you are using this VR headset, right? Is what this model can help guiding us to design better games, better eye head-based interface, right? This is basically all the research I like to share. Basically, some lessons that we learned is that VR AR is different from PC, right? So it's a new system that gives us a lot of research questions, right? How to make this system better while they are very close to the human. If you think about the difference between VR headset, they are also LED, LCD monitors in any sense, right? What makes them different is that they are so close to the human so that any small factors on the human perception is enlarged, right? If you took computer graphics courses, if you read OpenGL, you will know in traditional video game or any kind of graphics, 3D graphics, we treat the human eye as a pinhole, right? It's just a pinhole. I don't care, right? And then, but when this pinhole, this display is so close to our eye in a VR headset, the eye cannot be simplified as a pinhole anymore because any small subtle biological difference can be perceived, right? That gives us opportunity to actually optimize those computer graphics systems, right? Yeah. And also, if we understand better human, they can give us better performance of the device, better neural network-based representation for any 3D environment in teleportation, and better display stuff, right? So, and also, if we using XR device by understanding this correlation, we can make our decision making faster, safer, and make the ergonomics better in general, right? There are future research that I think is very interesting, right? So what if one day we have this computation not on device but in remote, right? And there are also visual, audio, tactile device while we are interacting with this, right? We have the vibrator, we have the spatial audio in VR. Any kind of auditory sensitivity is also different, right? That's pretty much all the research I like to share. And of course, all this research is not done by me. We have a great collaborations actually, including folks from Rochester, as well as my students. And I want to also thank the sponsors for all this research. Thank you.
Great. Now we want to ask some questions. If you, those in the Zoom, you can post your questions in the chat box, or maybe you can open your mic. Those of you who are in the room, you can also ask questions. So we already have one question from the back. Yes, I hope we can hear you. Just play like loud. Let's see if you can hear you. Yeah, I think. Oh, okay.
Hi, great talk. Very interesting topic. I was curious about the different kinds of, so you pointed out the use of like a NeRF model, a neural radiance field model to generate things like VR objects in real space. I was wondering, were there any kinds of pre-processing types of things that you had to do beforehand, or how that might compare to other methods like ray tracing?
Yeah, so basically you are referring to those, right? So how to have a better performance. Okay, so
Right.
here's the thing, right? So this is all frequent, great question in the first place, right? So you can consider that it's a different application scenario. Let's say with ray tracing, what's the input of ray tracing, right? So if you look at this image, right, what is the input of ray tracing? It's a 3D geometry. You have the mesh, you have the material, you have the texture, so that in VR, we can play a video game, we can do different tasks, right? That's the input. But the thing is, in what NeRF does is, you can, in physical environment, the geometry is very hard to acquire. In the state-of-art algorithm, you cannot reconstruct the perfect 3D geometry of the physical environment because there is always estimation errors. You cannot perfectly estimate, is this wood? What is a BRDF? What is a material? What is a norm map? Right? So very subtle, small differences. Right? This is very hard for physical environment. But what's the ground truth of the physical environment is I take my mobile phone, I take a picture. The measurement from the picture is always correct, right? So it's an optical measurement. There is no algorithmic estimation. And then the ultimate goal for this neural network-based rendering is, you can imagine in this case, I'm taking a few pictures. How do I have a representation of the whole room without this explicit ray tracing, let's say, right? And then they are, for one is for virtual environment, the other is for physical teleoperation. So the quality-wise, the ray tracing is highly related to your input data quality. If you give a messy, low quality, low poly mesh, however you do the retracing, the quality is bad, right? But NeRF is image-based rendering, so you can expect the original perfect quality in general, if that answers your question.
Yeah.
Performance-wise, it should be, because there's no free lunch, right? So performance-wise, of course, if you run the original NeRF, as we said, it takes probably 90 seconds per frame, which is actually comparable to a high-quality retracing, right? With probably 200 SPP, you still get like a minute to get the image. Right? So it's relatively comparable. But meanwhile, there's also research on foveated ray tracing, which is a side story. Yeah.
Okay. Yeah. Thanks.
Crazy. Any other question? Yes, Anish.
So I had a quick question. So great talk, by the way. I really enjoyed it. My questions are mostly kind of like in relation to eye tracking. So all of these would require eye tracking device. Is that correct?
Correct.
So I kind of have like two questions. So for one of the experiments where you were kind of like measuring the response before a saccade for the attention, what kind of eye tracker was used for that?
Yeah. So great question. Are you from neuroscience or visual science background?
Optics, but eye tracking, but I work on something similar, yeah.
Yeah. So okay, so if that's the case, basically what we were using the 200, we didn't require any high quality. We were using the HTC Vive Eye Pro. Back then, it was 120 hertz only, right? Today, you can easily buy a VR device with 200 hertz. The way we did the saccade onset detection was not by simply thresholding the velocity, because that would be too noisy for the consumer level eye tracker, right? So we were using the statistical approach that estimates how much standard deviation the velocity is from the mean value, so that it gives us a very robust estimation of the saccade onset. So it's both software as well as hardware combination.
Okay,
Yeah.
thank you. And then I had another question. So do you have any numbers in terms of like what the like spatial accuracy was for the eye tracker? So what kind of movement could you detect? Would it go down to?
Yeah. So I think measuring this device accuracy in-house is a research by itself, right? So how to characterize error. Usually the report from those manufacturers is, they call it sub-degree error.
Okay.
That's a statement, but in reality, the issue is for eye tracker, when you're looking at the periphery, the error gets higher because of the model and all that. So usually, while implementing those gaze contingent algorithm, we usually leave some buffer space so that it can tolerate the error. Usually, I think we leave about 1 to 2 degree space to accommodate that. And then but in this case, for example, the good part is we don't really care about your landing accuracy. We just care about your velocity. So by calculating the velocity, it can significantly mitigate at least the error from the spatial stuff, right? Because for example, if your eye is totally shifted, as long as consistently shifted, it doesn't matter. Right?
Okay, thank you.
Yeah, thank you.
Any other question? Anyone?
Just one in the chat.
So there's one in the chat. Do you want to read it out, Mr. Kim?
Okay, so I have a question on the NeRF 3D Gaussian splatting using VR, XR. I want to ask your opinion on the Gaussian splatting. NeRF was heavy to perform real-time in XR, but Gaussian splatting now achieves beyond 100 FPS. If that has changed any direction of the research, as the render speed and performance overhead has lessened much now. Yeah. So I think that's a good question. Thank you, Yang San. I think Yang San Kim from the Zoom is asking these questions. Yeah, great. Great question. That's why that research was done probably 2-3 years ago when the NeRF was originally presented as a representation. And in terms of the recent advancement of Gaussian splatting that can more efficiently encode and generate this real-time performance. Yes and no. The yes part is if you have infinite, that actually correlates to the two research between power and computation performance, right? If you have a monster GPU using the Gaussian splatting, yes, you can absolutely get a real-time performance. But in reality, if you think about the condition when everything is on an untethered device, the bottleneck is not just how technically, theoretically fast this can be computed, but of course, how much what's the best that I can get out of 1 milliwatt in general, right? So if your computation is infinite, yes, but on an untethered small chip, and then you cannot afford heavy computation, that becomes a question of, for example, what's the computation that matters more if you are capped by the computational source, right? There's still the redistribution of your resource kind of problem. Although the overall value can be pumped up, but it's shouldn't be in a uniform or constant way, right? If that answers your question. Yeah. Thank you.
I had a question.
Yeah.
Yeah, so when I use a VR headset, at first I feel fine, but after maybe like 30 minutes when I take it off, I feel a little bit sick. And likewise, I'm just curious on your work on the color perception.
Yeah. You mean this simulator sickness versus color perception?
So my question was on the color perception work that you've done. And did any subjects report discomfort from long-term use of this optimization technology?
Oh, you mean if you change the color if they use for a very long time, would that cause sickness? Is that what you're asking, right?
Yeah.
Yeah. No. I think our longest, the thing is, before you run a study as a developer, we test it ourselves, right? Unfortunately. But usually while you're debugging those systems, it takes hours and hours to test it. The thing is, I think the statement is altering color in the peripheral vision does not elevate the sickness level. Meaning if the person got sick due to other reasons, meanwhile, it doesn't help, but it doesn't introduce additional sickness. We have some research that I didn't get the time to discuss here is what is the source of the actual sickness, right? So usually sickness come from sensor conflict. For example, one case is car sickness, right? So while you read on the car, why many people got sick? Because your vestibular system, which is in your ear, tells you that you are actually moving in a car, right? Because that has nothing to do with your eye. If you're physically moving, you are moving. But while you're reading, your eye is telling you that you are seeing the static scenario. In VR, that's one of the sources. Let's say if you are using VR headset watching a roller coaster, your eye is telling you that you are moving really fast in this virtual environment, but your ear in your vestibular system is telling you that you are stationary. So there's a conflict, right? So that is one outstanding source of sickness. The other source is accommodation versus conflict. That's another optical reason. But the color perception wise, because the reason is we are using the altering is based on what people even cannot perceive the difference, right? If you cannot perceive the difference, that doesn't introduce additional conflicts between sensors because that's below the threshold that you can even tell the difference, right? So that's technically doesn't introduce additional.
Okay, thanks.
Yeah.
Thanks again for the talk. I had a question. I guess it's in my mind because of our last speaker was looking at essentially hearing disabilities in AR VR. Is that have you done any work looking at subjects who are colorblind? If this is a color filter, and if their experience is any way different from others, compared to regular users?
So for color blindness, I would since you are U of R, there are great experts in the university. One of my colleagues, actually today was giving me help me with a guest lecture on his research and color deficiency research, right? So I suggest to definitely consult with Yuhao as well. The short answer is yes. Before when I was working on, there were a lot of color deficiency features. Let's say in Photoshop, if you design a picture, how do you design this color perception? And then there are two sides of the question. The first one is how to accommodate the limitations of color deficiency. Do we need a new color model and color rendering approach, spatial temporal color rendering approach, so that the color deficiency people, with the help of augmented reality, for example, can see the color, can differentiate the color, not really see the color, but differentiate color better in the physical environment by this augmented filter, right? That's one exciting thing. On the other side, if you are referring to, let's say, the power saving model, the color sensitivity model, that is an interesting thing, because if you imagine the ellipse shape as a boundary, color deficiency, if you have a low performance in one of the receptor cells, the radius can actually get bigger. That means the range that the color can be manipulated is even bigger. So that can give additional space to reduce the color. And that's not only color. Many people have color deficiency at different level. Most of us actually are, right? Because of the sensitivity of the cells. And then the thing is, we measure a general population so that we took the most conservative range, so that we didn't take, for example, we took about 4,000 or 6,000 trials. We didn't take the average of the distribution. We take the most conservative range, so that it's statistically not assured, but improved such that it can work for the vast majority of population. But individual differences is actually considered there as well. But explicit study, I think, very interesting and useful for society.
Thanks.
Great. Dr. Chi, I have a question. I am a social science researcher, and I always worry about the environmental impact of technologies. So the thing is, like, you are working, your research actually focuses on how to reduce power consumption, and that's fascinating, actually. So, I mean, in terms of the significance of your research, like, how important do you see it is to reduce power? And recently, new technologies are coming in, Apple Vision Pro, more users, and also like AI is also coming in. And a recent research by Hugging Face researcher, they found that just training one simple LLM model is equal to million miles driven by a car. All right, so the carbon footprint we are leaving, I mean, of course, like we are having technological advancement, a lot of progress, but we are leaving a carbon footprint. I mean, we are also impacting the environment. So in terms of that, how significant is your research is?
Yeah, thank you, Manuel. Great question. The first answer is this: 60% studies show that 60% of the U.S. power consumption come from light, artificial lights, right? Display is one thing, but every single light consumption consumes about 60% of the U.S. energy. And the question, yes, this is starting. Like, for example, virtual augmented reality, the good part is it gives us a full control of what we can see, so that we can have a more controlled experiment to understand things in a mathematical way. But what about the physical environment, the physical light, right? So what are the imperceptible light usage that can reduce that? Is the first thing I think definitely exciting for like the physical space, right? So how to design a better lighting environment so that we do not overlight things as long as it passes the human perception. On the generative AI, that's come down to the similar to the nerve related research. I remember the blog saying generating a single picture with a generative model consumes the same power as a fully charged iPhone. Every single picture generation takes the same power. That means, yes, that a lot of computation is used beyond optics, right? So how to similar to this rendering world, right? So what pixels matter to humans? So for example, for any opticist, viewing science, you probably know the contrast sensitivity function, right? So our way to discriminate two different patterns is actually also limited, right? So what if we are generating something that is the same to human, right? So do we need to reuse the computation? That means it's also the opportunity to study, to understand the human perception into those AI models, right? Which is definitely exciting. What matters to human, what not?
Thank you.
Yeah.
Yes, Daniel.
Yeah, this is Daniel Nicole. Thank you for agreeing to give the talk. I was lucky enough to actually try the prototype last fall with the Fovio color distribution, and it's really interesting how little you can actually notice it unless you're making very rapid movements. I had a question regarding the first topic. I'm trying to wrap my head around the color space. If I'm right, the unique solution you described with the ellipses was particular for this display, right? And different displays are calibrated differently. So does that mean that you have to do this process for every display on different devices to be able to apply the algorithm?
Okay, cool. Great question. Thank you for asking that. Here's the answer, right? So the color perception is not really display dependent. What's fixed there in that study was the luminance level that we fixed. Let's say if you render an image with OLED or even LCD display, if the physical measurement is the same, they are basically generating the same lights into the eye, right? So roughly. Then we don't perceive or anticipate a bigger change among different display as long as you give the same luminance level. But in fact, what we intentionally did for that research was we were fixing the luminance level, because making image darker, of course, can reduce the power consumption, right? So, but darkening images is yet a different story. It's not really color perception, but also the luminance, brightness perception, right? We want to isolate the brightness perception from color perception by fixing the brightness level and study the color in that domain. That was an ellipse, right? But in fact, by different display, if we study all the conditions, that will become the ellipsoid in a 3D shape, right? If we consider a luminance level, that requires probably slice by slice by slice approximation in that regard. So that answer is yes and no, because that display has a range of brightness level, we fix it, but different display have different level.
Okay, no, that makes sense. That makes it significantly easier. But I presume for the third case, you do have to calibrate per device because the weight distribution on each display is going to be different. Right?
Oh yeah. Oh yeah, you're referring to that. Yes, exactly. Yeah.
No,
so
no, both. I was thinking about both. Yeah, both.
Exactly.
Okay, that makes sense. Okay, great. Thank you again for giving the talk.
Yeah, thank you.
Do we have any more questions in the chat? All right. So I would like to really thank Dr. Chi for your time. I mean, we really enjoyed, and we hope to see you in future in person in Rochester. All right. And if anyone wants to be in touch with Dr. Chi, I think you can find his contact info on our website. I have just given the link in the chat box. So you have information about our speakers, the previous speakers, as well as the upcoming speakers as well. Please check out the rest of the Voice of Excel speaker series and also the recording of the previous talks on the Studio X website. So that's all. Thank you so much, Dr. Chi. It was such a pleasure having you with us.
Thank you for coming to the talk. All right.
Thank you.
So have a great day.
Thank you.
Bye. Thank you. Bye.